Here is my tutorial on Unit 15 in Positive Chemistry. What you're going to need is your reference sheet and find the reactivity series here. I am in 1510, see that? 1510, reactivity series. This metal is more reactive than this one. Anything toward the top is more reactive than something toward the bottom. And these are considered essentially unreactive. If you just put these together, they won't tend to react much. Gold is famously unreactive. I'm not even sure what you have to do. I think you have to shove electricity in it to get it to react. People find gold coins at the bottom of the ocean hundreds of years later, unreacted. So let's go to problem 2. What's more reactive, copper or calcium? How should I know? We go to our reactivity chart. Calcium and way down here, copper. So calcium is more reactive. It can replace copper very easily. So let's go back. It is calcium. So can copper here do the reaction of replacing calcium there? And the answer is no, because we said it's less reactive. Copper can't replace calcium. Therefore, the answer is 4, no reaction. And I am right. Let's try this one. What's more reactive, potassium or copper? Well, I can tell you those alkali metals are very reactive, so it's going to be potassium, but we can check. Potassium is way up there. So it's definitely potassium is more reactive. Potassium. Now, that means potassium can replace copper, so the answer is not no reaction, because yes, it can replace it. If it replaces it, it is a single replacement reaction, and what would we get? It would grab the chlorines, and we would get +1, -1. That would mean we get KCl there. And you know what? That's enough of a clue, isn't it? Look, they have 2 positives there. That can't be right. And they have some weird mashup they invented there. This is the only one with +1, -1 together, so it's got to be number 3. And we're right. What's more reactive, nickel or chromium? Reference page. Nickel or chromium? Chromium is above nickel. So chromium is more reactive. So can nickel replace chromium? No, it can't. No reaction. What's more reactive, potassium or hydrogen? Well, potassium is very reactive, so potassium. Can potassium replace hydrogen? Yes, it can. In which point you would get Ki, because it's +1, -1, and only one of these has a proper Ki, and again, that has 2 positives together, so that is dumb. And the answer is 3. Here is 1511. I'm going to suggest that you get the ion chart that I made you, so it's easier to find stuff. Plus, get used to using this one for quizzes and such. What's the solubility of FeI2? Well, find the I- here. I- is soluble. It means it does dissolve. Hit pause and go find it. It's right there. And that means that things with that in it, I- tend to dissolve. And there are some exceptions to the right, but is iron one of them? Is that an exception to our rule? No, it's not. So this would be soluble. What about with lithium? Lithium is in my list of super solubles up here. So definitely that is soluble. Here, let's check. We're right. What about iodine? We just said iodine is, but guess what? Mercury seems to be an exception. So I'm going to try the insoluble here. I was right. Silver is an exception to iodine. Look to the right, and it is insoluble. We're right. Lead, too, is an exception, so it is insoluble, not dissolvable, or pretty much not dissolvable. For all practical purposes, most times. Magnesium, I do not have as an exception, so I'm going to try soluble. And I was right. See, chart works. Let's try another one. How about CO3? We have that on here? We do. I have carbonate down here in my insoluble group. But look at the top, the very top there, above the chart, I have a list of super solubles. Anything with potassium in it is soluble. Anything with NH4 ammonium in it is soluble. Do I have any exceptions to carbonate? Not really. Look to the right of the carbonate, and it says slightly soluble. So I'm going to try slightly soluble for rubidium with carbonate. Oh, they want insoluble. Okay. Excuse me, I am wrong. Rubidium is also a super soluble, so that makes it soluble there. Carbonates come up as basically slightly soluble, and iron does not change that. We're going to try slightly here. We're going to try insoluble here. There we go. Okay. We're at a little bit of a guess there, what they want. Or you can use their solubility chart. Remember, we're not grading on the accuracy, just whether you got done eventually. I'm going to try insoluble there, and nickel is not section anything, so insoluble. There we go. I'm in 1512 now, and we're going to do double replacement reaction, but you can say that you can make these things, but will they actually stick together in water? And once you've gotten a little familiarity with this, some of these will become a lot easier. What I have here is lithium in my first salt, plus minus pair salt, but lithium is in my super solubles. Guess what? So is NO3. So both of these have a super soluble, which means neither of these will actually stick together in water. And if they don't stick together, then nothing really got made because you put in the left side, it all comes apart, you mix it all up, they, at least on paper, it looks like they trade partners like we did before, but will they really stick in real life? And if you get two solubles, that means that you can say they traded the partners, but nothing will actually stick. So which of these are insoluble? Neither is insoluble. Both of them will still dissolve. So if nothing dissolves, then we don't get a solid. See, these S's are solid, and AQ means aqueous, dissolved in water. Think of aqua, water. So all three of these claim that one of these will be a solid. That one says that one, and this one. So each one of these has a solid, but that is not true, in which case nothing really sticks together. Nothing really, really happens, even if you write it on paper that way. And no, there is no reaction. Womp womp. So we learned that K is a supersoluble and rubidium is a supersoluble. So neither are, sorry, both are, neither, sorry, is insoluble. In which case there is no reaction if nothing's actually going to stick to each other. Now, rubidium is a supersoluble, so that's right that this is aqueous. That is wrong because rubidium can't form solids in water. That is wrong. And so is it no reaction? No, because something will stick, I think, the aluminum, the hydroxide. I think so. But it's certainly not these two. That's wrong for sure. Let's go look at hydroxide. Hydroxide is there. It is insoluble. It does not like to dissolve. Hit pause, go find it. And aluminum is not an exception to the rule. So it does not like to dissolve. It will form a solid. And so we need this one not forming a solid, staying aqueous, and this one being a solid and actually sticking. So which ones are insoluble? The aluminum with the hydroxide. And that means that number one had it right. What we have here is cesium, and I think that's a super solid. It is super soluble, excuse me, super soluble, which means it does need to be aqueous, which means that's wrong and that's wrong. How about SO4s, though? Do they make solids? SO4s are... I think we're going to... It's right there, sorry. They are soluble, but is calcium an exception? It is an exception. So most of the time they are soluble, but with calcium they are not. In which case they don't dissolve and they do make solids. So this time number 1 has it right. So which one was insoluble, doesn't dissolve? The calcium one. And we said number 1 had it right. Now I'm on 1513. When you dissolve plus minus pair a salt, the ions come apart. So is this aqueous? Yes. So they come apart, and look, there are the two of them. We don't have any solids. They are both aqueous. There we go. And when these dissolved, they came apart. And when this was a solid, it did not come apart. It is a solid. Doggone it. They said solid. They're right there. And because that is aqueous, because remember, it has a super soluble in it, NO3, they did come apart, so they are apart. And we're right. So what didn't change? What was a spectator? What just watched everything happening? These two here, these two, I can't highlight them. The barium and the nitrate didn't do anything. They started out aqueous. Look, the barium's aqueous, the nitrate's aqueous, and they ended up aqueous. So they didn't do anything. They didn't participate. They just watched. So the silver did participate because it went from aqueous to solid. The barium didn't participate because it went from aqueous dissolved and it stayed aqueous dissolved. So it's just a spectator. The nitrate did the same thing as the barium, and the chloride went from aqueous dissolved to being stuck in a solid, so it did participate. So let's mentally cross out the spectators. We're going to cross out the nitrate and the barium, which means the real reaction that really happened involves only the 2 silvers and the 2 chlorides and makes that. So we said the barium's out, so that one's wrong. We said the nitrate's out, that one's wrong, right? And this is just everything all together. And so it involves the things that didn't really do anything. This is the one that really got made, because remember, we're crossing out the barium and the nitrate, which leaves just that one. So the answer is 3. So this was aqueous and it dissolved, so they are apart. This is aqueous, so it's dissolved, so they are apart. This is aqueous, so it dissolved, so they are apart. It's the aqueous. Notice not apart and solid. That would be wrong. They are dissolved, and this is a solid, so it stayed together as a solid. There we go. So what happened here? Only the vanadium and the hydroxide did anything. They were aqueous, and now they are a solid stuck together. The bromide and the cesium were both aqueous, and now they are still aqueous. So the cesium did not do anything. It just watched. The vanadium did participate. It got stuck to the hydroxide. They both participated in the reaction. And the bromide did not do anything. It was a spectator. Yep. There we go. So what's the real reaction? It's only the one involving the vanadium and the hydroxide. And that is number 4. Now I'm on 1514. What type of reaction is this? Well, you can look down and sort of see that we're dealing with a single replacement, aren't we? The lithium is trying to replace the hydrogen. So it's a single replacement, and it's replacing the hydrogen. I don't know why they care so much about that part, but there we go. So what do we look at? Can the lithium actually replace hydrogen? And you're not expected to remember. Let's go back into our reference to our reactivity series. Well, lithium is the most reactive thing, so it can replace anything. So can lithium replace hydrogen? Well, of course it can. So it is not no reaction because yes, it can do it. What would it do? It would stick to the bromine. So that is wrong because that's two positives together. That is just a big mash of everything together, which is dumb. This is two positives together. And this is everything broken apart where the lithium didn't stick to anything. So that is dumb. So also this is, yeah, that's two positives. So what could it have made? The lithium could have replaced the hydrogen and stuck to the bromine. So the answer is 4. We have strontium trying to replace copper, as you can see here. Can it do that? I think so, but let's check. Strontium trying to replace copper, yes, it can. That is reasonable. So, and it's a single replacement. It's, I guess, a metal replacement. There we go. So can it do it? Yes, it can. It was above it on the reactivity series. So it is not no reaction. This is just everything stuck together, which is stupid. This is two positives together. That is two positives together. And this is just everything split apart, so that is dumb. I think, see, two positives together, everything together, which means this is the only one that makes any sense. Where the strontium really did replace the copper, and the answer is 4. This is a double replacement because we have the Na. Whoa, I can't get it. Whoa, buddy, it doesn't want to do it. The OH is the right half, and the Na is the positive half. The Br3 is the negative half, and the gallium is the left half. So could they trade partners? Well, what do we know? Sodium is a super solid. Soluble. Excuse me, I keep saying super solid. Super soluble. Way up there. So you can't stick stuff to sodium in water. You can't do it. So anything with a sodium solid is out. That is wrong. That is wrong. That is wrong. And sodium solid by itself is wrong. This is dumb. So I just said no, 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 no. So it's either 1 or 4. Does gallium hydroxide make a solid? Well, hydroxides tend to be insoluble and make solids, and gallium is not an exception. So I think it would. So I think our answer is 4, and it's a double replacement. We got a precipitate, we got a solid. A precipitate is a solid, precipitation falling out. The solid would fall out in the beaker. Like precipitation, like rain, snow, sleet, hail, etc. If you look at this, this would be, again, a double replacement. And we're not doing, actually, this is an acid and a base. This is giving an H to that one. Because look, when you give an H away, that's an acid. When you take away an H, that's a base. So when you put H with OH, as we said before, you get water. And so this is going to be a double replacement where the acid and the base are neutralized. That is L in the parentheses for liquid. That is not 1. That is L for liquid because water is not a liquid. Water is not dissolved in water. It is water. So it's a liquid. So will we be making water? Yeah, clearly. If you put an H, an acidic H with a basic OH, yes, you will certainly get water. This does not get water, so that is dumb. This is no reaction, so that is dumb. Solid water is ice, and that is stupid. And this is just, well, the chlorine broke off by itself and stuff, and that's not what's going to happen. So we've kind of proven our point, but let's go into, well, no, it's one of these two, right? So will a cesium salt be aqueous? And cesium is one of our super solubles. So yes, it will be aqueous. So they're both right there, but cesium is a +1 element, +1 charge, and chloride is a -1. So if you have 1 and 1 plus 1 minus 1, you would get one of them and one of them, and not Cl2. So that is wrong. So the answer is 3. This, I think, is just a double replace. Are we forming a gas? I don't think so. I don't see any gas. G for gas. This is just everything broken up, so I don't think that's right. And, oh, sorry, we are forming a gas there. Let's see if they want gas formation. They do. All right. The H could stick to the S because that's a +1, and that's a -2. That's fine. And that could be right, and that could be right, and that could be right, so that's fine. This is just everything broken up, just dumb. And if you get a gas, then something did happen. As we talked about at the very front of the whole class this semester. So it's not no reaction. So it's not 1, and it's not 6. Will you get any water? Well, there isn't even any oxygen in there, so that is dumb. So it's not 2. Will zinc chloride be aqueous? Apparently it will, because look, all 3 of them have that. But what's the relationship, the ratio between zinc and chloride on your ion chart? Zinc is +2, chloride is -1. So you need to have 1 zinc and 2 chloride, which means only this one is correct.